we've already done a lot of work to introduce this idea, okay? So a lot of you could probably guess what's going to happen next, right? There is one and only one kind of equation, kind of function, okay, that fits this description. There's only one kind of function such that when you differentiate it, right? Now we're talking in actual calculus language. When you differentiate it, you get back a version of itself, just off by a constant. There's only one function like that, and it is, well, the aptly named exponential function, right? It's where this number comes from, okay? We define this number, the way we got it, is by thinking about something that's growth rate occurs in relation to its size, okay? So, the exponential equation. P equals. Now, I'm going to describe this in a second, but let me finish off the sentence. The exponential equation, such, right, is a solution to and by the way, it's important that you phrase it this way, okay? Especially, it's not the solution, because there are others, aren't there? What kinds of other solutions might we introduce? Because we're starting with a derivative, right? And I want the primitive, we know there's a whole family of primitives that would all fit, right? You could add a constant onto here. I'm going to let you have a think about why, at the beginning at least, we're not going to talk about that constant, because adding that guy on, he makes things behave quite differently, okay? We will get to him because you guys are extension students. Just out of curiosity, students do not. This is the limit of exponential growth indicator that they address. But this is a solution, okay? So let me give you an example, okay? How does this thing work? I give you some numbers. Actually, I'll say a question to you. I want you to put your pens down, and then we'll write down all the numbers together. So here's the situation. A town's population, we're talking about population when we were saying this, right? Town's population, one day, 5,000 people. 5,000 people, okay? 10 years later, it's 7,000. 10 years later, 7,000, okay? Now, if we assume that the population grows at a rate that's proportional to its size, which is a reasonable assumption to make, okay? It's kind of weird to think just, it trickles in at a constant rate. What would that be? 200 people per year or something like that. That's not the way populations tend to grow, okay? So if the population is growing in this way, what will the population be 5 years later, okay? Now, there was the idea. Let me get down all those important details again. Where did we start? How many people did we begin with? 5,000 people. Okay. After how long? 10 years? What was the population? 7,000. Okay. And we assumed that what was joining these two, okay, was this idea, this proportionality growth type. Okay. So now my question is, what happens after another 5 years? Okay, so what we're doing here is we're modeling, okay? We've got a situation and we're fitting equations to the situation to see if we can predict something. That's what modeling does, okay? So, being that we've got this, okay, part A of a question like this would usually be to do this, okay? And how do we do it? I know it seems a bit trivial, but you have to start this way. You would say, part A, let P equal. Now, in a second you'll work out what these letters are. K we've already introduced as this constant that tells us how fast things are happening, okay? In a minute, you can tell me what capital A is, okay? But first, we want to show that it fits the information that I've been given, that it does grow in this way, proportional to its size, okay? How would you do that? How would you show that this satisfies this? Okay, I want to differentiate, get a left-hand side, and then have a look at the right-hand side, and I should be able to show that they come to the same thing. Okay, so I'll say, therefore, dp on dt. Okay, so I'll differentiate. What happens to it? Yeah, it's chain rule, isn't it? The k just comes out the front. There you go. Left-hand side. Okay. Right-hand side is kp. Okay, well, we've just defined it like this. You're like, really? That was it? Yes, that was it. Don't take any shortcuts, okay? So, dp, oops, sorry. This satisfies okay? So I've got my starting point. The one I'm going to use for my model does fit what's required of me in the question. Okay, great. Let's move on to part B, which is working with this, okay? How am I going to move from this, which is all abstract, has nothing to do with a particular situation, and deal with the information they've given me, okay? Think of these all as points in time. Think of them all as points in time, okay? So, this is my starting point, right? Let's call that time 0, because that's where we've begun, okay? When t equals 0, okay? The population is 5,000. Okay, so I'm going to use this equation which I've introduced and fit this information in. Okay, let's do it. 5,000 equals AE to the K times 0. Okay, so what does this mean? A is equal to 5,000. Okay, now it's for this reason, right? A, why do we call it A and not like B or C or D? Does sound cool, doesn't it? A to KT just rolls off the tongue. We call it A because A is the first letter in the alphabet. It's your starting point, okay? Alternatively, and you will see it just as frequently said, not necessarily A to KT, but P equals P naught e to KT. Why do you think they give that? Because it's a population at time 0, okay? You will see both of these equally frequently. Okay, good. Now I've got a value for A. How do I need to progress? I'm trying to get towards something over here, right? What would I do next? Well, there's another constant in there which I do not know, right? Namely, K. By the way, because that K is there and it defines this equation, it's also called the constant of proportionality. There's a lot of words and phrases in this subtopic, and that shouldn't surprise us because this is not just maths, this is the application of maths, right? So interact with the real world so you get lots of words, because the real world is full of words. All right, how are we going to work out K? How are we going to work out K? We've got another point in time, don't we? Okay, so instead of being the initial condition, t equals 0, I should say when t equals 10. The population is defined, they tell us it's 7,000 at that point. Okay? So, let's take that, fit it into our model, and see how it helps us. Okay? What do I get? 7,000 equals, here's my value for A, right? And there's my 10 up there. Yep? Now I want to make K the subject. Okay? So what will be the nice first step? Divide by 5,000. Get 7 on 5. Yeah? Now what? Okay, we can convert this to a log equation, or alternatively, if you want to think about it that way, you can take logs of both sides. Okay, when you take it on this side, it becomes that. When you take it on this side, the e to the power of just disappears, right? So you get your 10k. Is that right? So now I have k on its own. Now, it bears mentioning that at a lot of questions at this point, they'll ask you actually to give me a decimal for k. I think it's 0.033, something like that. But you don't have to. You can leave it exactly. That's quite nice. Okay. Is that right, by the way? Someone want to chuck in a calculator? Yeah. Okay, great. Now, how am I going to use this thing? I've got all my constants now, right? I have my a, which is actually just the initial population. I have my k, which tells me how fast this thing is growing. The number's quite small. Right? That corresponds to the fact that really, even though this growth is proportional to how big it is, it's not super fast, is it? Right? 10 years and that's all you grow. We're not used to thinking of an exponential growth being this slow, but it really depends, really. Why don't I do that? If you draw an exponential graph, right, it sort of just depends on how far you zoom in, right? If I zoomed into here, for instance, okay, it'd look pretty slow, but it's still exhibiting the conditions of being proportional, its growth rate being proportional to its size. Okay. All right, I'm ready to put this in. What do I want? I want t to be 5 years further, which is 15. Okay, so I'll come to my population equation, which I now have all the pieces for. It's 5,000 e to the k, this, times time. There you go. So what do you got there? I'm going to put this into decimals because it'll be easier to do. 1.5 log 1.4. Okay? So you got a choice at this point. You can get your calculator out and you can chuck that in. If you remember your log laws though, you might notice that that's the same as saying 5,000 e to the log 1.4 to the power of 1.5, which is the same as 5,000, that e to the log. They actually just cancel each other out. So that's actually 1.4 to the power of 1.5, which is somewhat easier to put into your calculator. But either way, what do you get? Eight thousand?
Yeah,
282. Now what's the decimal? 0.51. Okay. ... I have a question for you. We're talking population, aren't we? We're talking people, okay? Now, very interesting. What does this mean? What does this mean? It's a boy. This means we're at a point where, obviously, because we're talking in years, right? So we're expecting this not to give us an exact number, right? This graph here is continuous. So all the way along here, you've got time this way and population this way, right? You've only got that very limited number of spots that are actually whole numbers, and everything else you're in between, okay? So, should we round up, because it's a 0.5, or should we round down? Down? Seem pretty, what's the word? Unanimous in that, okay? Now, here's the interesting thing. You really can do both. That's a bit of a dangerous thing to say. In terms of population, right? Remember what I said at the beginning, okay? What were we doing? What's this process called? It's modeling. Modeling, right? No one in their right mind thinks that this is actually giving you the exact number of, ta-da, at the end of, you work out what hour it'll be when the 8,283rd baby pops out, okay? That's not what we're expecting, okay? We know it's an approximation. We know it's an approximation, okay? You can actually say, well, suppose it was something like 0.9. You're like, what am I closer to? Well, I'm closer to 83, aren't I? And it's just an approximation. It's tell me roughly how many there are, right? Rounding down is also fair because you don't have a whole person yet, do you? Okay, so you can say that and that is just fine. Okay. Nearest person, they're all the same. Okay. Now, I could have started here, couldn't I? Could have started here and said, look, let's go, let's just use the equation. I want you to get in your head though, why we introduced the exponential, right? It's all about this guy. This is the real hero here, okay? It just so happens that this is the solution to that, okay? But the idea of exponential growth is all about its proportionality, okay? If you understand that, the rest of the topic will fall out.